In this video, I'll talk about the reactions of organometallics with epoxide. Now, remember, we know when we talked about the epoxide in general, we know the epoxides are very unstable, even though you can make them, but they're relatively unstable because of the ring strain and the angle strain that they got both of them in there. And in a typical epoxide, let me just kind of go ahead and draw that here. I got an oxygen and two carbons in a three-membered ring, so I got a ring strain here, because a typical stable ring is a five-membered ring and a six-membered ring. So we got a ring strain and we got an angle strain. A typical tetrahedral angle is 109, but here it's actually going to be 60 degrees, so that puts in a strain on this molecule. And on the top of that, you also have this carbon oxygen bond where carbon is going to be partially positive and oxygen is going to be partially negative. So for that reason, I can have some sort of nucleophile under basic conditions to attack one of those carbons and open up the ring. And if I was doing this under acidic condition, I would go ahead and protonate that oxygen first. So for that one, you may want to watch another video where I have just talked about the ring opening up the epoxides under acidic and basic conditions. Here, we're just primarily going to be talking about how the organometallics can be used to open up the ring. So what we really get from an organometallics is just an nucleophile, is just a carbon-based nucleophile. And indeed, it is in a strong nucleophile. So as a result, when it comes down to do the attack, it's gonna attack the carbon that's gonna be most readily available. So I can say that, okay, I got this carbon with a positive charge and this carbon with a positive charge, but the carbon on the right side is more readily available or less sterically hindered. So having in a strong nucleophile, the strong nucleophile is going to go ahead and attack this carbon, and it does do in a backside attack. That's another thing you want to kind of keep in mind. I can probably just go ahead and draw that down here. So it does the backside attack in a sense that it does not want to come from the same side where the oxygen is, because remember the oxygen is also carrying two lone pairs, so it doesn't want to come from the same side. As a result, it comes from the backside and it breaks this carbon-oxygen bond here. And then what we really get at the end of the day. Now, since I'm doing in the backside attack here, it inverts the stereochemistry of this carbon, but it does not change the stereochemistry of the other carbon that is not attacking. Now, this carbon actually is not really chiral to begin with, so I don't really have to worry too much about the stereochemistry on this carbon. But if this was, then I would have to flip the stereochemistry. So whatever this originally was, like if this was like suppose R, then I would change to an S and vice versa. But in this case, this is not chiral, so I don't have to worry about it. So how does the product going to look like? So I want to kind of leave the skeleton momentarily as it is. So I got this bond here. And I want to go ahead and leave this oxygen here. When that breaks open, I'm going to have an O minus there, and I'll leave this methyl just like it was before, because I'm not changing or altering the stereochemistry on that carbon, just on this one, but this one wasn't really chiral, so I don't have to worry too much about it. And then I'll ended up getting a new bond formed here from the bottom here, and that would have a CH3 here. And I don't necessarily have to write down the CH3. And again, this is not chiral, so I don't want to worry too much about the stereochemistry on that right carbon. But then remember, the left carbon kind of stays the same in terms of stereochemistry. And the second step is just the protonation, dilute acid, and it would go ahead and put in a OH there. So if I want to go back and look at the RNS on those, so let's say the RNS, change the color here. So on this one here, I would call this to be 1, 2, 3, and your hydrogen seems like it's already going back on the page. So that's going clockwise. So 1, 2, 3 going clockwise. That's going to be an R. So I want to make sure I don't change the stereochemistry on that. And turns out this is going to be still 1. That's going to be 2. That's going to be 3. Your hydrogen is still back in the page, so that would still be in an R at the end of the day. If I was attacking the carbon that was actually chiral to begin with, I would have to invert the stereochemistry. So like, for example, in this second question here, I have a Grignard reagent. So obviously I'm getting a carbon with a negative charge, so carboanion from that Grignard reagent here when I break the carbon-magnesium bond. So now between the carbon on the left and on the carbon on the right, I want to say that I would be attacking the carbon on the right again because it has only one R group as opposed to carbon on the left actually has two R groups. So it's more sterically hindered on the left side. On the right side is less sterically hindered. So as a result, when I do the attack here, it's going to be doing a backside attack onto the carbon that's on the right side, and then that opens up the ring in this particular case. So I don't want to change any of the stereochemistry stuff on the left carbon, so keep that in mind. So I want to kind of leave the O minus there. I want to leave this metal coming out of the page. I want to leave this isopropyl grip coming out of the page, and the metal is going back in the page rather. And then on the right side, I want to somehow flip the stereochemistry, and there's like different ways of drawing it. So what I can say is if I go back and be like, all right, this one, when I number this out, that would have been 1, this side would have been 2, this side would have been 3, and your 4 is the metal, so it's already going back in the page. So that's an R. And then one on the right side, I get this to be 1, I get this to be 2, and I get this to be 3, and your hydrogen is already back in the page, so I don't have to flip it. So it's going counterclockwise, so that would be an S. So I need to make sure I draw an R there, and there's like different ways of drawing it, but as long as I get an R, that's really all that matters at the end of the day. So I can go ahead and show that I got this bond here that we just created. So because I just put in a methyl group in there, and then what else I got? I got the metal. So I want to probably flip that for a minute. And if it does not come out to be right, you can always change it. So let's say I'm going to go and flip that for a minute and make the hydrogen come out of the page. But always, you can flip it if it does not come out to be right. You want to double check here if it comes out to be right. So if I want to go ahead and count those out, now this time I want to call this to be 1, call this to be 2, call this to be 3. So that's going counterclockwise, but then you got to flip it because your hydrogen is coming out of the page, so it's going to be an R. And that's what I really need at the end of the day. So if you think of this, this was originally an S. I want to kind of invert the stereochemistry. That's all really matters at the end of the day. And it doesn't really matter how you draw it as long as you draw an R in there. That's all that matters. And then I want to leave the left one as the same. So left one, if you count the electrochemistry, or if you do the chirality on there, that really had stayed the same on that one. So that one would still be in an R. Because that's 1, that's 2, that's 3, and that's 4. Okay, so then I want to go ahead and protonate this using the second step. So acid water or dilute acid will do the job, and I'll end up getting an OH there. And that's pretty much it. So at the end of the day, you want to make sure you keep track of where this organolithium or organometallics carboanion would attack the epoxide to open up the epoxide, and it's always going to go to the carbon that's less sterically hindered at the end of the day.